video, we're going to talk about the distribution of the sample mean. Let's consider the following example. The weights of pennies minted after 1982 are approximately normally distributed, with the mean 2.46 grams and standard deviation 0.02 grams. So that describes population. So consider all pennies that were minted after 1982. The fact that mean, and notice how we're using mu, right, for population mean. Population mean is 2.46 grams. It means that you can think about it as the average weight. And then sigma, it stands for population standard deviation. It equals 0.02 grams, and it describes the spread of this distribution. In other words, it describes the variability in the weight. Let's say that we're going to obtain 200 random samples of size 5. So here's an example of one of the samples, right? Size 5 means that I have 5 pennies in that sample. Each penny will have its own weight, right? And, they're all different. They might be the same, but they also could be different, as we can see in this example. And this is one of 200 samples. So for this specific sample, the sample mean, which we denote by X bar, right, is 2.444 grams. So that means that the average weight for those 5 pennies, if I add weight of all those 5 pennies and divide by 5, I'll get 2.444 grams. And now sample standard deviation we denote by lowercase s, right, is 0.02 grams. Now what's going to be important to note is that if we take different sample of size 5 different coins, so if we randomly select 5 different coins, well, this information will be different, right? Sample mean might be different, most likely it will be different. And then sample standard deviation most likely is going to be different. And that's important to understand, because pennies will vary from sample to sample. The sample mean and the sample standard deviation of the weights will also vary from sample to sample. Now we said that we can obtain 200 random samples. Let's right now focus only on sample mean. We saw sample mean of this first sample, but we have 199 more samples. I'm going to show you this table. So what we have here, we have the first 100 samples and their corresponding sample means. So the first sample, that's the one we looked in the previous screen, right? The first sample mean is 2.444. Then we're going to take another sample of 5 coins. Its sample mean will be different number, and so on and so forth. So as we obtain simple random samples, their mean values are different, right? And they're all listed here for the first 100. But remember, we talked about 200. Well, I have another table that has 100 more values, and again, these are sample means. This all together creates sampling distribution of the sample mean, X bar. So we can see how sample means, they vary from sample to sample, so they create its own distribution, right? So as we look at this list of numbers, which are, once again, their sample means from 200 different samples, it would be interesting to know, well, what's the average of all those numbers? So it's like, what's the average of all those averages, right? What's the mean, in other words, of the sample mean? And here's that question: what is the mean of the 200 sample means? Well, if we calculate it, right, if we take those 200 numbers, add them up and divide by 200, we're gonna find that it's 2.46 grams. And note, it happens to be exactly the same as the population mean. And this is how we're gonna denote it. We say mu with the subscript X bar, and it's 2.46 grams, which is the same as population mean. How about the standard deviation of those 200 samples? We know that numbers vary in the table, right? They're slightly different, but how much do they vary? What's the standard deviation? Well, if we calculate standard deviation, we can just take calculator and use that for calculating standard deviation. We're gonna find, for those 200 samples, or sample means, I should say, that standard deviation is 0.0086. And now note that it's smaller than the population standard deviation. So while mean of the sample means was exactly the same, standard deviation is less. What does it mean that standard deviation is less? How do we analyze the results? Well, we know since sample we know since standard deviation measures the spread, greater standard deviation indicates greater spread. So the fact that standard deviation of the sample means is less than population standard deviation, it means that sample means are not as spread out as the weights of the coins in the population. And that should make some sense, because if we consider all the original coins in the population, well, there are some extreme values, there could be some extreme values, like coins that are much heavier than the rest of the coins, and then coins that are quite lighter than the rest of them, even though majority of them are around the mean. But as we create samples, and if it happens that extremely, and it's all of course relative, right? If that extremely heavy coin that we had in the population gets into the sample, and we then calculate sample mean, then sample means themselves will not be that extreme, right? Because the heavy coin in the sample will be balanced out with the coin or coins that are not that heavy. So sample, we're not going to see that extreme values when we look at the sample means versus looking at the coins themselves. And that's the reason why standard deviation is actually less. Standard deviation of the sample means is less than population standard deviation. Now, how do we denote this number? What's the notation for standard deviation of the sample means? Well, that's going to be notation down here. So we're going to use sigma for standard deviation, but it's special standard deviation. It's standard deviation for the distribution of sample means. So that's why it has subscript x bar. The picture on the right-hand side, it illustrates what we just talked about. It illustrates that for a population, which is this blue line, mean will be the same as mean for the distribution of sample means. They're centered at the same value, 2.46. However, as we can see that population distribution is wider, right? It's much wider than distribution of the sample means. It means that the weights of the coins within the population have more variability, they're more extreme values than when we look at the sample means. So we're not going to find that much variability. That's why the spread is smaller. And we can confirm that by looking at the numbers. Population standard deviation is more than standard deviation in the sampling distribution. Next, it's going to be interesting to ask what role does n, which is the sample size, right, play in the standard deviation of the distribution of the sample mean. Remember that we just tried samples of size 5. Like, what happens if we increase sample size? How will that affect the standard deviation of the distribution of the sample mean? In other words, will we see more extreme values in the sample means or less of the extreme values? And this is how it works. As the size of the sample increases, the standard deviation of the distribution of the sample mean decreases. So it means that as we increase the sample size, we'll see less and less variability in the sample means. They're going to be less and less different from each other. So let's try to change the sample size to 20. So now we have 20 coins in each sample. Well, we'll find that the mean of 200 samples, now for the larger sample size, is still 2.46 grams. But the standard deviation now is 0.0045. So it's even less. Let me summarize all that. So what we want to note here is that, again, distribution of the spread is, so as we increase the sample size, sample means will be closer and closer to the mean, to the average. So as expected, there is less variability in the distribution of the sample mean when sample size is larger. And now let's summarize that. So based on the statistical history, this is what we know. So the sampling distribution of the x bar, which is sample mean, has mean. So again, let's think about it as like taking average of averages, equal to the mean of the population. So that means that we only need to calculate it. If we know population mean, that we right away know the mean of the sampling distribution of x bar. How about standard deviation? We notice that it changes, right? It depends on the sample size and it changes. Well, we'll need to use a little formula to calculate standard deviation of the sampling distribution of X bar. And that's how this formula looks like. So to find standard deviation of the sampling distribution of X bar, we have to take population standard deviation and divide on by the square root of n. So that is the sample size. And that's where sample size will mathematically take effect. Larger this number in the denominator, well, smaller overall result we'll get. And that's going to be consistent with what we talked about. Now, this standard deviation has another name. It's called standard error of the mean. And finally, we're going to read one important theorem in statistics. It's called the central limit theorem. And this is what it says. It says that regardless of the shape of the underlying population, let me make connections to our example. So remember how we talked about coins, and population of coins minted after a certain year. So each coin has its own weight, but we know that weights are different from each other. But we don't know what kind of shape the distribution of those weights has. So is it are they normally distributed or not? Or maybe they skewed left or skewed right. We don't need to worry about that. Basically, this is what the theorem says, because regardless of the shape of the underlying population, the sampling distribution of X bar, those sample means, right? When we create a list of sample means, the distribution of sample means becomes approximately normal as the sample size n increases. So larger sample size we choose, the distribution of sample means will become closer and closer to the normal distribution. And what does this mean for us? Remember, normal distribution is somewhat easy to work with, right? We have z-table, we have technology like calculator to answer a lot of different questions about normal distribution. So theorem really opens doors for us to answer many questions about sampling distribution of X bar, which is sample mean. And we're going to try a few examples in the next video.